Okay. Thanks, Atul, for inviting me to talk in the seminar. It's always a pleasure to be able to talk to one of our own. And okay, so the title today's talk involves the subject called Liouville quantum gravity. And I'll spend some time, I would like to, because this is one of the areas in contemporary probability theory that has seen enormous amount of work in the last decade and in recent years, and is still ongoing. And it has brought together ideas, intuition, insights from several related areas of mathematics, and has turned out to be one of the most productive and rich areas of research in modern probability theory. So I'll talk about mostly about some of the results that are not mine. Anyways, any case, this, well, I worked for, as part of my thesis in my PhD long, that was like 5 years ago. And then again, there's a short one that I did this year. But I think what's good for all of us, I guess, just to be a bit familiar with what happened. So this is a work with Zerifan. He's a PhD student at the University of Peking. Okay, so let's start by addressing the elephant in the room. What is Liouville quantum gravity? Okay, so this thing originates in physics. So roughly speaking, it's a one-parameter family of random fractal surfaces. Again, don't worry. I mean, I'll soon make these things as precise as possible, given the time frame. But so one-parameter family of random fractal surfaces, which was first studied by physicists. I think the earliest work dates back to a very celebrated paper by Polyakov in 1981. It's called Quantum Geometry of Bosonic Strings. It's a very celebrated paper. As a class of canonical models of random two-dimensional Riemannian manifolds. Okay, by the way, just one disclaimer. Please don't ask me what is that got to do with quantum gravity and things like that, because anyways, I'm not going to be able to give a very satisfactory answer to that, but at least I can point you to right references. So what is it? So formally speaking, it's imagine you have a surface. You can imagine the sphere, but imagine the complex plane equipped with a volume form, okay, the analytic tensor, okay, which is essentially kind of conformal to the background metric, your flat metric, but it's the conformal factor is given by exponential of gamma times h. What is h? H is an object, and I'll not go into details, but I'll discuss a bit in the forthcoming slides. It's what is called a Gaussian free field. Okay, you can imagine Gaussian free field in a sense, if you think like it's a canonical Gaussian process indexed by a plane, in a two dimension. So in one dimension, it would be like Brownian motion. It would be like a analog of that. If the parameter space is, instead of being just a line, one-dimensional line, it would be a surface. Okay. And the parameter gamma, so in this way, in this parameterization, it would be anything between 0 and 2 real interval, or it could be any complex number with absolute value 2. Okay, it could also be complex. And I'll talk about that. And it already raises some questions. I know, like, okay, what does they for me? And that's the point, actually, why we're giving this, we're talking about this in the mathematics colloquium. But roughly, this is the picture. So that's great. And so what have mathematicians got to do with it, in particular probabilists? Well, the thing is that this is not well defined. Why? Well, because h is not a function. Forget about continuous function. It's a random scores distribution. Okay, it comes from putting a probability appropriate way, probability measure on the space of scores distributions. And you can deal very nicely, actually, the theory of squares distributions or generalized functions, for that matter, is the linear theory. Okay. And making sense of a nonlinear function of that, like exponential, it's something that calls for new ideas. Okay. And you have to make sense of it in a big way. Okay. So, so before going to this next slide, let me tell you that how did probabilities enter the picture. It turns out, okay, so the idea is that, well, you have a scores distribution, and what do mathematicians do, and especially analysts, and I'm speaking to, especially when I'm speaking to people from TIFR CAM, they would know this more than I do, is that you first mollify it, right? You mollify it with respect to bump functions, okay, with the shrinking support, let's say. You do that to get a well-defined function. Okay, and then maybe you can define, so for each such, each with the modification comes a threshold, right? It's a parameterized kind of like a threshold, because it depends on the radius of this bump function, essentially, the support, radius of the support of the bump function that you take with respect to which you modify. And you can define something, so, you can probably make sense of this thing. Essentially, what you're trying to make sense of here is a metric measured space, by the way. Okay, so this is the volume form, and there is an associated metric. Okay, there is an area form, and there is an associated. So we want to make sense of it as a metric measured space. So probably then you can mollify it with respect to a threshold, let's say epsilon, and you get a family of metric measured spaces. And maybe you can take their limits in certain sense, certain suitable topology, and that would be a way to make sense. Non-trivial limit, of course. Well, okay. Now, it turns out that making sense of the area, actually, what is called the Liouville quantum gravity area, that's easier of the two tasks. Okay. By easier, I don't, by no way it means I'm saying easy. It's very difficult, and it involves sophisticated mathematics, but it's easier compared to the metric, which actually most of the talk will be devoted to. In the probability literature, it was started by through the work of for the area form, area of LQG, started with the work of Duplantier, and Sheffield, Scott Sheffield, where they made sense of the area form by using a apparatus, which kind of probably they independently discovered, because it was actually done before, but it's not quite well known, called Gaussian multiplicative chaos. It's essentially a theory of instead of additive noises that we are mostly aware with, like Brownian motion and things like that. It's a multiplicative theory of Gaussian noise. So you take exponential of Gaussian and multiply it at different scales. So that was done by Duplantier, Sheffield. And then from the metric side, the first breakthrough came through the work of Jason Miller and Scott Sheffield through a series of breakthrough papers, but using exploiting a different connection. So they made sense of it as a metric measure space, but exploiting a different connections. So this comes from as scaling limits of random planar maps. So random planar maps, again, I will not, that will be too much a tangent to this talk, but you take, let's say, a sphere, and you say that, okay, you fix the number of faces, which you let go to infinity, and you fix a particular type of polygon, let's say triangle, and you put uniform measure. Okay, you can put other measures also, but let's say for this one, the relevant one is a uniform measure on all possible ways of triangulating the sphere, modular orientation preserving homeomorphisms. And this gives you a metric measure space. Then actually you study the Gromov-Hausdorff limit of this space. So the limiting object, the limits of this kind of this random planar maps was discovered to be, and precisely described, very explicitly described, so-called Brownian map. by Geoffroy-Legal independently. Around the same time, Geoffroy-Legal and Gregory Miermont around the same time. What is actually missing, of course, to identify, to relate it to the, because it was long conjectured that so the gamma equals to square root of 8/3 is mysterious, but actually it comes to the fact that it is related to another parameter in physics called central charge, which is 0, which the idea is that it should come from a limit of random planar maps when you take uniform measures on them. Okay. Anyway, so this connection was in these papers by Miller and Sheffield, they established a deep connection with this Brownian map for this particular parameter, gamma equals to square root of 8/3. And they precisely described this limiting metric measure space and also described the conformal structure, which is also a very inherent part of this whole LQG story. But this approach was essentially confined to this particular case. For general gamma, an alternative approach was started, kind of like, I would say initially, kind of like the program was started by Jiang Ding, using a discrete approximation of the metric by the so-called Liouville first phase percolation. So let me describe that. So how does this first phase percolation come into the picture? For those of you who know, otherwise I'll again describe it. Okay. So again, let's just make this thing precise. So you take what you're taking is a whole plane GFF. Again, GFF is the way I explained it is a canonical random scores Gaussian process, but which is essentially again a random scores distribution. I'll not go into very detailed definition of GFF, but many of the properties will be unearthed through the talk. But you can imagine it's like a Gaussian field. If you think that the pointwise variance is kind of like infinity, but you can make sense of covariances, which decays like the Green's function in dimension 2, okay, 2-dimensional, the log potential. By the way, I'm cheating a bit. Whole plane GFF is not again a distribution also per se. It's a distribution modular and additive constant, but let's keep that aside. That we can take care of other ways. So this is what happens. So you do the modification in the obvious way. And of course you have to prove that you can make sense of such modifications, but that you can do. What do you modify it against? You modify against the heat kernel. Okay, this is a standard heat kernel, where the dispersion factor is like epsilon square over 2. So imagine that it's like the heat kernel describes the density of the Brownian motion, dimension 2. So taking it epsilon square, it means essentially that it's essentially concentrated around the ball of radius epsilon. Okay, because of the Brownian motion is diffusing. So that's the thing. We're essentially kind of modifying it over a region of radius epsilon around it. So that's what we're doing. So this gives you a well-defined function. It's Holder continuous and everything, modulo normalization. So now you define this metric. What do you do? Well, first, what you do is that you take a path, take 2 points Z and W, and take a path, any piecewise, let's say, rectifiable path P, okay, or let's say piecewise C1 path P. And what you do, you define the length as you do if you're working, let's say, on a Riemannian manifold where the metric is being dilated by this factor. Okay, here you see the emergence of a new term, new kind of parameters, xi, okay, which is not quite same as gamma. I'll explain that later, but let me tell you what this is related to. You see, when you're doing classical Riemannian geometry, right? So the length element and the area element will be dilated by different factors based on the area, okay? And so that's the thing here. Well, if I was working with the setup of classical Riemannian geometry, this xi would be just gamma over 2 because we're in dimension 2. But here it will not be the case. It turns out to be, it has to be fixed, but it will be what should be divided by, it should be the Hausdorff dimension of the underlying kind of metric space that we're going to construct. I'll come to that later. But its exact dependence on gamma, it's not known. But it would be this gamma over the Hausdorff dimension of the underlying metric space. Okay, the limiting matrix. Okay. Anyways, it is another reparameterization for the moment. Let's just think about it, which is good for making sense of the metric. So you define the lengths in the usual way, and then define your distance to be the length metric. You have defined the lengths of paths, and you define the length metric space, which is just taking the infimum of such length over all piecewise C1 paths connecting C and W. So that's your definition. Why is called first versus percolation? So for those you know, in a probability theory, it's a very active area of research. Is a very rich model of random matrix on graphs is the first versus percolation. So what do you do there? Imagine, let's say you take a hypercubic, let's say Z2, the lat is simple Z2. There are two versions of it, one age version and one kind of like, sorry, one vertex version. So for us, it will not matter. So what you do is that, let's say the age version. So to each edge, you assign an independent and identically distributed non-negative random variables. Okay. And then using these variables, you can define the length of a path, let's say any path, by summing over this random variables, the non-negative random variables attached to each of the edge that appears in the tag. That gives you a notion of length, and you you define the distance between these 2 points to be the length of the minimum path, where length is defined in this fashion. Okay, this gives you a kind of a random metric space on graphs, and this is well studied in this classical setup when things are IID. This is a well, this setup of course is anything but IID, but you see the reason is that what we are essentially doing. So instead of H, you could also assign this weights to vertices. And essentially, if you think in the discrete terms, where essentially what we're doing is that for any path, we're essentially kind of summing up the weights attached to the vertices. Okay, so that's sort of the connection. Okay, so that's the definition of the metric, which is modified at level epsilon. Okay, so far so good. So now, how to get a metric out of it? Like how do you actually plan to make sense of this limiting LQG metric? Well, so here is a question. So we want to take a scaling limit. So let's say so what we want to ask is that if there are some scaling factors which will depend on psi, this parameter, and epsilon, of course, so that if you normalize the metric by this normalizing constant, then it will converge in some appropriate topology to some non-trivial random metric space. Okay, that's the way we are looking for. So the first result that came in this regard was by Jian Ding and Alexander Dunlop back in 2016. So again, I'm stating this for this version, but it was done for what's called a discrete Gaussian field, but everything can be subsequently generalized. But the definition of the essential model, the underlying models, derivative model doesn't really matter here. What really matters is strength of the result. So what is this lambda xi epsilon? Essentially, it is chosen so that the median left-right distance between, let's say, two sides of a box. Okay, let's say take a box of side length 1/3. Doesn't matter. It's like 1. Okay, so it could be any quantile. These things are pretty well concentrated. So you took that to be your normalizing constant. Okay, so you normalize the left-right distance essentially of a compact set, let's say of square, and then for small xi, very small values of psi, so they call it like high temperature because it kind of like appears as if like the temperature parameter, inverse temperature parameter in models and statistical physics, converges subsequentially up to subsequences in the Gromov-Hausdorff sense to a random metric on V13, where all the limiting metrics, which was at that point of time only conjecturally unique, are equivalent to the Euclidean metric. Okay, so that was the first result that was obtained. Okay. Similar tightness results was subsequently obtained by Duveta and Facone in 2018. for metrics arising in similar way from what they call the star scale invariant fields. Essentially, the Gaussian free field or the dimension, they have a certain hierarchical structure. So you can essentially write it as an independent sum of fields, where each field in higher scale is kind of formed by it's an independent copy of the field at the lower scale, subject to some dilation, kind of like scaling in terms of the output. Anyways, also in the same year, again, and that is also an important thing, because remember, we have to make sense of this limiting space as a metric measured space. And the measure, as I told you, the area measure has been already been explained by the work of Duplantier and Sheffield. So there is another way you can also make the notion of a distance by ball covering number. Okay, where balls come from. Okay, so what does it mean? Essentially, is that there is another way you can define a distance, is if you know the area measure, is something like this. So take any 2 points, Z and W, and what you do is that you try to cover this up with balls, let's say. With balls, so that the LQG area of each of this ball, the LQG area, which has been made sense of, as I told, of each of these balls is at most some delta. Okay, delta is again analogous to this threshold parameter epsilon. Okay, and what you do is that you try to look at the minimum number of balls of area at most delta with which you can cover, essentially cover a path between C and W. Okay, this is a notion of metric that is coming from the area measure, and you can easily convince yourself, like, you know, let's say just in Euclidean plane, how this also makes sense. Anyways, again, so they did that for it is called the Liouville graph. This is for the subcritical range gamma and 0 2. Now, the tightness of LFPP in the full subcritical range was finally proven in a breakthrough paper by Jian Ding, Julian Dubeda, Alexander Dunlop, and Hugo Facone, with the parametrization, as I was telling you, gamma over d gamma, and lambda, this normalizing constant, as I was defined as the median of the left-right distance of a square, is given precisely by this number, which is 1 minus, but what is the parameter? It appears as psi, and a parameter q, which is related to kind of like variable change in this LQG business. That is no, okay, so that's related to gamma by this nice formula, which is 2 over gamma plus gamma over 2. So it's coordinate change formulas in Liouville quantum gravity. Anyways,
Subhajit?
Yeah.
So if you go back to the previous slide where you talk about covering path with balls.
Yes.
So that reminds me of some sort of an entropy that is usually associated with the Gaussian fields. And there, if you want to approximate, you have to have some sort of a scaling, right?
So, okay. Of course, all of these things are relevant, but okay, I'm not sure exactly how what you were meaning there. But so these balls, you see, what I told you is that you have already an LQG area that is described, okay, with respect to this Gaussian free field, continuum Gaussian free field. So that you have it. So you know the area form, area there.
Yes.
And what you do is that, well, what you say, like in a, let's say in an Euclidean plane. So, if you just do this thing, I guess it depends, it will scale with the underlying dimension. But I think, so for example, if you take 2 points at a generic point, the optimal covering would require like delta to the power 1 over 2. It's kind of like optimal covering of a path, geodesic.
Precisely, but the delta to the power of 1 over 2, that 1 over 2 is very crucial in this.
No. Yeah. So that absolutely, you're absolutely right. So, and that will involve things involving d gamma. And things
I see. Okay.
Yes,
all right.
yes.
Thank you. That was my
absolutely.
question. Okay,
Yes.
thank you.
Yeah. Absolutely. That's why actually these things come. Because the LQG area is just defined with respect to gamma, and how actually suddenly, well, then when you switch to this first passage percolation mode, how does the 1 over d gamma come? It's basically precisely from that kind of connection. Of course, you have to make sense. Thanks. Yeah, so that's exactly how it works. Okay, so yeah, I think what I'm going to say next is also pertaining to your question, that the gamma is the Hausdorff dimension of the plane with respect to the gamma Liouville graph distance, which is already defined and established by separated with Ding Juan and Ding and Yan Juan and Ding Zertini and Fuxi Zhang in 2018. And just a side comment, they also proved that Ding and Juan in 2018 that this is kind of really like a reparameterization. That gamma to gamma, this psi, this map is really a reparameterization, at least in the 0,2, the subcritical range. Okay. Now, you have proven the tightness of the matrix, tightness, essentially. So you have proven that subsequential limits exist. Now, how do you show that there exists one unique metric, essentially, up to some suitable normalization? So this was pioneered by this works by Yuan Juan and Jason Miller in a series of papers, and then also Duveda, Fakone, Juan, Pfeffer, and Sun. So the strategy is twofold. First, what you do, you try to, and it actually draws on some ideas already contained in the paper by Jason Miller and Scott Sheffield that I was referring to earlier. The idea is that first you try to characterize all possible limiting metrics, okay, through a list of axioms. And if I get time in my talk, I'll show you a snapshot of this. So you try to characterize through a list of axioms, and you show that all possible subsequential limits satisfy each of those axioms. That's first. The second part, and all of these are contents of different papers, long, different, difficult papers. The second part is that you show that, and which is completely nothing to do with this approximation, that these axioms uniquely characterize a metric. Okay, combining these two, you get the existence of a limiting metric along with some interesting properties. Well, this was for gamma in zero in the subcritical regime, and where all the metric, this metric that you get is essentially bi-ellipsis equivalent to the Euclidean metric. No, I'm sorry. I take that back. No, that cannot be true. Absolutely not, because that will actually nullify whatever I'm going to say now. So it's bi-Holder equivalent to the Euclidean metric. Okay, that's the thing. It's a bi-Holder equivalent. So it's the same topology. As a consequence of that, you immediately get by Hopf-Reno theorem that you have a locally compact complete space, and you can also prove that there is a length metric space. So the existence of geodesics are confirmed. Anyways, for gamma equals to 2, which is a critical case, it is more difficult. The limiting metric, okay, and the supercritical case is the most mysterious, where gamma is complex, but you can still make sense of this psi parameter. Psi becomes like arbitrary, the big positive numbers. Okay, this program was carried out on subsequently by Jian Ding and Juan and Pfeffer in 2020 to 2021 time period. And so let me just tell you a bit small trivia about the topologies. So for the critical case, so this case, gamma equals to 2, the limiting metric is still homeomorphic, like it's still equivalent to the Euclidean metric, but it's not bi-Holder equivalent. Okay, it's becoming more and more singular. For this one, the twice the circle is just my poor way of writing that complex number with absolute value 2. Then what happens is that the limiting metric is no longer even is not equivalent to Euclidean metric at all. In fact, actually, there will be almost surely on a dense subset of points, the pairwise distances will be infinity. Okay, so it will be a very singular metric. Okay, so that's the metric. But with on a measured zero set, by the way, outside the singular points, it's well defined and complete. Okay. Okay, so now actually I'll go to the today's content, but before that, are there any questions about the definitions and so on? Okay, if not, anyways, I can come back anytime. So let's start with the content of today's talk. So, as I told you, in the subcritical case, proving that existence of geodesics is quite straightforward. just apply Hoff-Reno theorem. But for higher it is more difficult for general gamma. But they have been done. In fact, actually also it has been proven they're unique by work of Jason Miller and Wei Qian. And also in another recent work by Yu and Joanne, by Joe, let me just write that, by Joanne Pfeffer. So I just have to check that whether I did don't get the spellings wrong. Yeah. And of course Sheffield. It was proven that there exists a constant delta geo. Okay, this is a constant. Let me just check it again. Yeah, this is deterministic. So deterministic, that's important. Such that with probability 1, all geodesics starting from 0. Sorry, what happened? Sorry. Did I do something? Okay, I'm sorry. I don't know what happened. Sorry for that. Okay, geodesics starting from 0 doesn't. Okay, well, by invariance properties, translation invariance for income, starting from 0. Okay, so this is so is that for the Euclidean Hausdorff dimension it's important to say Euclidean Hausdorff dimension because you see it's if you have geodesic space, then of course the Hausdorff dimension, it's a topology, the Hausdorff dimension of geodesics with respect to the underlying metric, the LQG metric would always be 1. So there is nothing there. That's always true. So it's the Euclidean Hausdorff dimension. Yeah, so there exists a constant LGO. Everyone already. Okay, sorry. The statement doesn't make sense. Yeah, have. It says 0, 1. I have Euclidean Hausdorff dimension delta G. Okay, so we know that there exists a deterministic constant, deterministic Hausdorff dimension for all LQG geodesics starting from the point. Okay, and as to the value of delta geo, it was expected that well, it is strictly bigger than 1. And let me tell you kind of why. It's because typically the LQG distance between two typical points is well, of course, it depends on what scaling you take, but in an appropriate notion, is much smaller than the Euclidean distance. Okay, and this fact actually was utilized by Jian Ding, again in a different work, Jian Ding and Fuxi Zhang in 2019, I think. Let me check this again. Yes, 19. To show that well, as soon as you have this kind of property that you have your length exponent, the distance between two typical macroscopically separated point is below, it's sublinear in the Euclidean distance, in a sense. Then what you'll have is then your geodesic has to have a Hausdorff dimension strictly bigger than 1. Okay, because you have to essentially wiggle a lot in order to gain such things. And then what they did, they used a result that I proved with Jian during my PhD, where we showed this thing. It was kind of like refuting a long-standing physics conjecture that it will be really sublinear, that the typical Euclidean distance typical LQG distance between 2 points with appropriate, when you scale it appropriately. But which is still till date only known to, okay, I guess, yes. Essentially, except for other regions, we do work of UN and Joshua Pepper, that for small values of the parameter psi. Okay, so that was only known from small values of parameter psi, but it was also actually done in a certain sense for LFPP distance because the metric, this limiting metric, was not known back then. So
Subhajit,
yeah,
when you say it was observed or it was known that the distances were smaller than the Euclidean distance, how were they known or how were they observed?
Oh, no,
in
no,
sense
okay.
Like numerical?
Okay, so so there was a conjecture actually in physics called Waterpicky's conjecture for a long time that gave a precise formula of the Hausdorff dimension of the metric d gamma, and using the connection that I just told you, you see, if you remember, okay, let me just show you that again. So the Hausdorff dimension is related to the distance exponent in this way.
Correct, I remember.
Exactly, from which there actually
Yes.
you can conclude that it would be less than 1.
I see.
Basically, yeah.
So your delta, so your delta geo is not only larger than 0, but it's larger than 1, you mean?
That's the content of today's talk.
I see. Okay.
That's the content of today's talk. Yeah.
So, okay.
So that's what I proved in this paper. Yeah. It was a kind of like it was going on like a folklore statement in the community that it would be proven, but like, okay, but and how long it would take, because the proof by Ding and Zhang was pretty complicated. Again, they do it for LFPP, and also it works only for Z small, very small. The situation hasn't changed because they depend on something, a condition that is still not proven. Okay. So now actually, since I have let the cats out, so let me write the basic theorem. So the theorem is let's say sorry, by myself. Let H be the whole plane GFF, and DH be the associated Z Xi LQG metric. Then for all psi bigger than 0 with probability 1, the Euclidean Hausdorff dimension of any, just highlighted that, any DH geodesic is strictly greater than 1. So there are 2 questions. One is obvious that comes from this, is that what about a quantitative bound? Does the proof give a quantitative lower bound? It does, but it's not good. It's far from what we expect to be optimal, and it's an open question actually to be able to find, at least to a good extent. So the bound that we get, lower bound, is so let's say it's like 1 minus. Let me check. That's right. Yeah, 1 plus e to the power minus c to the power z to the power minus 2. Okay, there is something moral in this thing first before actually, but it's nonsensically small. You see, this is getting worse, kind of like it's going to 1 as xi goes to 0, and that should be expected. When xi goes to 0, you are just in a Euclidean setup. it should be closer to 1 as I goes to 0, which you can read off from there. But it shouldn't be so small. We don't expect that because this behavior is not correct. Right. And the second question is that, well, there are different versions of the Gaussian free field that goes around. Like sometimes, like if you don't take whole, you can take a subdomain or different subdomain of C, where you consider GFF. But all of our result extends to all of those things by local absolute continuity. Essentially, all these GFS locally are absolutely continuous. Okay, since I have in the remaining 15 minutes of time, let me try to outline the main steps of the proof as much as I can. Okay, so how do you actually kind of try to prove a statement like this, that that a system, you have a system of curves, and you want to prove that the dimensions of any one of them is strictly bigger than 1. Well, the basic picture is that, okay, they should wiggle it somehow, right? A lot. They should, at least when going from one to other, it should wiggle in a sense in every scale. They're fractal in some sense, in a correct sense. How to quantify that? Well, the quantification would be something like this. You can say that if you put rectangles, let's say, or let's say thin annulus, maybe that's also kind of bad. So let's say you have different sizes of annulus, certain aspect ratio. Sorry. Yeah. So on and so forth. And what you do is that you say, well, the idea is you want to kind of measure the departure from being straight. So here is what we do. Well, a straight line, or if a curve is regular, it will kind of like, well, traveling from here, let's say to here, it will essentially move through this angles. Okay, it will go to the inner circle, let's say, if it wants to go to a diametrically opposite points. So what you want to do, you want to say that, well, the probability that a path in your random system of curves crosses a number of such annuli, they can be located anywhere, but let's say they are always at a certain distance from each other. Let's say the distance between every pair of them, they're all separated. So the distance between every pair of them is proportional to the maximum of their diameter. And then what you want to do, you want to obtain a bound on the probability of such events. How? A precise criterion was given by Aizenman and Burchard in a very famous paper in 1998. The paper is called, it's a Holder regularity and dimension bounds for random curves. But they showed, okay, if you can do this, you can show that, well, for any pair, let's say, of such family of annuli, okay, which are well separated, and let's say their number, so they are, like, say, any numbers, then the probability that any path in your system will traverse through each one of them decays geometrically in the number, exponentially in the number of such points, number of such annuli. The thing is that this will not hold for our case. This is just not true. And the types of systems that Aizenman and Burchard had in their mind when they're writing the paper are, like kind of like level curves or the interfaces in critical percolation, systems like that, which will essentially converge to SLE-like curves in the light. Okay, and where they have a very inherent independence, spatial independence, which you don't have for Gaussian free field. But what we figured is that you can actually do a bit better. You can actually do without that. And we have a certain kind of, we have a theorem is that, well, while you cannot prove it geometrically, you can prove something like this, a modified version of that. Again, that again, I'll not precisely describe what families I take. Let me just, but still give you a very like a picture description. So we'll consider a certain family. We'll not consider any families of well-separated annuli, but we'll consider some, a bit restricted, is that your family has a hierarchical nature. So what do I mean by that? Well, the radius of the balls, this are the annuli that you take, and take this to be a fixed aspect ratio. So let's say the inside one is always like the half of the, so this is like R/2. Sorry, this is like R/2, and if this is okay, and okay, so what you do essentially, imagine essentially your collection of annuli, you can group the radii of this annuli into scales which are roughly decaying faster than geometric. So if you have a scales like indexed by positive integers, so let's say LK1, which is like L0 to the power some lambda to the power minus K1. So Kj, let's say. So Kj's are positive integers, and lambda is bigger than 1. So roughly, you have some separate scales, K0 less than K1 less than K2. Don't have to be consecutive, but roughly the radius of any annulus within your family would have a radius roughly like LKJ, up to constant factor, and the number of times, the number of annulus with the radius within a given range, which is close to LKJ, would be roughly same. So we call this family of balanced. But then, the main theorem from which actually our the main proposition from which our theorem follows is the following: that there exists a parameter rho psi belonging to strictly less than 1. That's important, such that for any collection of disks, and then the bigger disks, so that is and then the big good. So
I think some problem with connection.
This number is
Let me chat him.
geometric scales in which there is arranged. Sorry.
There was some problem with the connection. We did not hear the last line.
Oh, okay. So did you hear this lambda mu good?
No, we did not.
Okay, I'm repeating. Sorry for So okay. So but you can see it, right? Again.
Yeah. Now it's good.
Okay. So okay. So the proposition from which our main theorem follows is the following: there exists rho in 0, strictly less than 1, depending on psi, so that for any collection of disks that are lambda nu m good. What I mean by that, as I essentially explained, so these are these 3 parameters associated with such families of balls. So lambda is this thing, which is essentially kind of this geometric, this factor bigger than 1, which kind of separates the, which controls the geometric rate of decay of the scales. K1, K2, Kms are the basically this scales at which around which at which we find the radius of the balls there. So that's M. And nu is basically, as I told you, for each Kj, there will be a certain number of balls. There has to be a certain number of balls in your system, and that number, like, okay, not exactly, but up to a constant multiple is nu. So that's exactly what is a good family. So for any such family that is a new group, one has probability that DH geodesic crosses each annulus. Sorry, that's just my notation to annulus corresponding to agent is bounded by. Sorry, let me just but anyways, let me write the bound big way. Some constants times rho, which is not quite exponential, but not too bad. And turns out to be enough. Okay, so again, what I mean by process is essentially this picture that you see. Okay, so the idea is that it will go from one end of the bigger disk to the other end. While doing so, it will intersect the inside ball. Okay, now let me quickly describe just for one ball why you do expect for one ball it essentially means that the probability is strictly less than 1. And to do it for a number of balls, you need to go through greater technicalities, but that is unrelated to the is mostly related to the property of GFF, not Gaussian GFF, not the LQG. But let me just quickly try to describe what is happening, the main picture. Okay, I'll try to be quick. So here's what happens. Sorry, let me just use this one. Okay. So what do we want to do? I want to prevent a picture from some. Okay, I want to say that with a positive probability first, just for one ball, a geodesic will avoid. Sorry. Okay, a geodesic will avoid this inside ball of radius half. So the probability of that. So the probability of this happening is strictly bigger than 0, but not just that, it's something that only depends on psi. That's important. It doesn't depend on scale, point, and whatever else. Okay, how you can do that? So the idea is when actually such a thing can happen. Well, here is a possibility. You draw two further annulus around it. Okay, I have to finish, I guess. So just be quick. So this is another annulus, imagine. And there is another one that I have to draw. So this one. It's going to be tricky. But I will not draw the full one, but imagine, so you have this two disjoint annulus which is between these two. Okay. Now, if it so happens that the distance across this inside annulus in the LQG distance is more than the distance around this orange annulus in the LQG distance, okay, then of course it makes much more sense that for any path, so since it's geodesic, remember, they minimize the length. So it doesn't make sense for the geodesic to come all the way to here. Rather, what you would do, because when it's coming, when it is crossing this one, it is essentially incurring a bigger distance than going it around. So it would be much more economic. It would be economic for the geodesics to go around it. So it would rather do something like this. So the geodesic would rather be this than going through, going through this inside ball. So you have to show that the probability that the distance around this orange annulus is more than, is less than the distance across this inside annulus has a positive probability independent of the size of the point. And that you can show using, as I was telling you, the LQG axioms that I alluded to, and the scale invariance property of the Gaussian free field. So roughly what happens is the following, and there is actually comes the main picture. So this family of distances around and across, they're tight random variables bounded at infinity. So what we can do is that there is a positive probability. There is a positive probability that, well, the distance across this orange annuli, sorry, around this orange annuli, is at most the distance across this this inside annulus times some big positive number. There is a positive probability of that. That's great, but you cannot just do it with big positive number. You have to do it with exactly 1. But then there is a one part of the axiom, which probably, let me just take this opportunity quickly to show you. It's called locality. It's taken from a paper, which is the fact that when you are confining yourself to a domain, so this is the thing, deterministic open set, then your internal metrics, so the metrics that are just coming from considering lengths of paths contained within that domain, is entirely determined by the field restricted to that domain. Okay, it's internal, it's a local with respect to the field. So what does it tell for us is that what you can do using property, what you can do is that we can add a bump function. Essentially, we can add a bump function to the Gaussian field so that we can make the field in this little inside annulus very high, up to a, depending on as much as you want to do. And the cost of doing that, the law of this resulting field is absolutely continuous with respect to the original Gaussian field by Cameron-Martin theorem. And you can actually explicitly compute that cost, by which cost is something like that is by the scale invariance property of scale and translation invariance property of Gaussian field. Doesn't depend on Z or R, like the center, the Z or the radius. It just depends on the underlying parameter Xi of the LQG metric. Okay, so I think I have already 1 minute passed, but okay, so once you do it for 1, this gives you the fact that, okay, rho is something which is positive. It's just a positive number for 1 ball. Then how do you get from there to there? Well, if you had things like independent, of course, you could just immediately say, well, okay, I mean, I just multiply these probabilities. Gaussian field is like anything but independent. They are actually, if you take their finite scale approximation, finite threshold modification, their correlations decay very slowly, actually. It's logarithm in the inverse distance. But so there actually comes in the next picture, which is that, well, while they are correlated, but the correlation is essentially carried by what is called the harmonic extension of the Gaussian field, which is again a distribution, but well, from the boundary to the inside. Okay, so you can write the Gaussian field when you have such a separated families of balls into sums of independent Gaussian fields with the which is supported on each of these balls. Let's like this picture, and on top of that, an independent field which is harmonic, and smooth inside the balls. Okay. Now, what's the advantage of that? Well, it turns out, you see, that our entire argument is essentially based on comparison between distances. Okay, their ratios. So if the harmonic what you can apply using Harnack-like estimate, that the harmonic function is very smooth, kind of like very flat when you are away from the boundary inside these balls. So you can, then what it boils down to is that you have to control the fluctuation of the this harmonic field across all such balls. And that's where this reduced cost, this suboptimal kind of like subgeometric cost, sub-exponential cost comes, this exponent comes. Okay, because the other part of the field, which I described to, which is Gaussian field supported inside each such ball, they are independent, and that gives you an exponential decay. The entire correlation is carried by this harmonic, controlling the fluctuation of this harmonic field, and it's based on this observation that while the harmonic field is, of course, that can be very big, so you cannot control that, but you can control this fluctuation, and that's the only thing that matters to force these events with the arguments that I just outlined, because it all boils down to comparison between distances And so just like in Riemannian metric, if you multiply everywhere by a constant, the ratios of pairwise distances just remain the same. So you can just replace constant by something which varies very slowly, and you're in good shape. Anyways, so last part was a bit hurried. I agree with that, but I'm open to questions if you have any.